Let's delve deeper into the theorem of substitution with definite integrals. This method aids in simplifying integrals by substituting variables to make the calculations easier. By redefining the variables we work with, we can transform complex integral expressions into much more manageable ones. We will explore this concept thoroughly through a detailed step-by-step example, enhancing our understanding with practical application. The theorem states that for a continuous function, if we define a new variable based on another differentiable function, we can leverage this relationship to simplify our integral calculations. This change of variables is crucial as it allows us to evaluate integrals more systematically and efficiently. Understanding this theorem is vital for proficiency in calculus, especially when dealing with definite integrals. Now, let's solve the integral of x squared from 0 to 1 using the theorem of substitution. This is a practical example that will allow us to see the power of substitution in action. In solving integrals, identifying a suitable substitution is the first and crucial step. It involves selecting a new variable that makes the integral simpler to analyze and solve. In this case, we propose letting u equal x cubed. This choice arises from considering the relationship between the function we are integrating and the concept of differentiation. The indefinite integral of x squared is closely tied to the cube of x. Thus, this substitution feels natural. Once we assign this new variable, we find a new differential relationship between u and x. Specifically, when we differentiate our substitution, we discover that do is equal to 3 times x squared multiplied by dx. This redefinition effectively transforms our original integral into a much simpler form involving the variable u. As we use substitution to change our variable, we must also adjust the limits of integration. When x is 0, u will also be evaluated at 0, maintaining consistency in our integral. Conversely, when x reaches 1, u will equal 1 cubed, which is 1. This procedure of adjusting limits is crucial to ensure that our integral represents the same area under the curve we